Charles Elton. And he was the first person to sort of propose the structured ecosystems representing the energy in sort of this pyramid form. So you could blame Charles Elton for these Eltonian pyramids that have appeared in ecology. And what he's trying to do, or what he tried to do, was represent the law of thermodynamics in an ecosystem in a graphic way, a way that was sort of immediately obvious to everybody. Of course it's not, but that was what he was trying to do initially. So in Symmutex, we had pyramids that were sort of based on sort of three different possibilities. We had pyramids based on energy availability at each trophic level. So here, we saw the Sankey diagram for this Silver Spring, Florida, done by Andrew Odom. Plants, in terms of the amount of energy, make up 20,000 plus kilocalories per square meter per year. Okay, so this is going to indicate a rate of energy production. There's a decomposer pathway over here, which we'll sort of skip for now. And then over here we have our primary consumers, things like insects and snails, eating about 3,000. I'm sorry, not eating, but representing 3,000 kilocalories per square meter per day of energy. Fish that feed on them representing about 383 kilocalories per square meter per day. And then up above them, carnivorous fish and predatory fish representing a grand total of 21 kilocalories per square meter per day. The idea is every time you've got insects eating plants, or fish eating insects, or fish eating fish, there's this net loss of energy that's associated as you move from one level of the pyramid up to the next level, up to the next level. We can contrast sort of this energy pyramid with it's called a biomass pyramid, represented up here. And a biomass pyramid looks more like some sort of summertime lawn game than an actual pyramid. Seems a little awful skinny. The idea here is we're looking at the amount of biomass present on a per area basis. There's no rate associated with which energy is being produced. So instead we have plants here representing 809 grams of probably carbon per square meter. Snails and insects, 37 grams. Fish, 11 grams. And then predatory fish, 5 grams. In the middle here are these sort of number-based pyramids, which I absolutely hate. And if I could rip them right out of Symmutex, I absolutely would. These are put in largely, nobody actually uses these at all in research, but I think this is probably shown for the sole purpose of saying, like, the number of individuals at each trophic level doesn't necessarily correspond to the amount of energy at each trophic level. So for example, over here in a temperate forest, on a tenth of a hectare, so about a quarter of an acre, we have 200 trees and 150,000 herbivorous insects and 120,000 predatory insects and 5 birds. Not terribly informative. The one thing that's important to recognize with these pyramids is you, as a reader of these diagrams, are at first going to want to ask yourself, what is being represented here? Is it biomass that's being represented, or is it energy that's being represented? So is it biomass or is it energy? And there's a very quick way to determine what's being represented. If it's biomass only that's being represented in a pyramid, your units are going to be some sort of measure of mass per unit area. So in this case, we have grams per square meter. So mass per unit area is grams per square meter. That indicates you're looking at a pyramid based solely on biomass. However, an energy pyramid is going to have the amount of energy available per unit area, so per square meter, but there's also going to be a time component, so per day or per year. it's going to indicate the rate at which energy is being produced in that system. Not just the amount that you find now, but the overall rate of productivity in that system. So our representation here is showing not just that plants have 20,810 kilocalories per square meter, but that's basically what's going to get renewed every year in that system. So that's fundamentally rate of production. And it's important because as you get into pyramids, you can sort of see weird things happening. For example, if you're looking just at the biomass, you can get inverted pyramids, often in aquatic systems. So here we have a situation where in an aquatic system we have very little phytoplankton, so primary producers. And so you might have, I'm going to try to scale this mentally associated with the size of the blocks. You might have 100 grams per cubic centimeter of phytoplankton. And you might have 200 grams of zooplankton per cubic centimeter eating that phytoplankton. And you might have an even greater number of small fish eating those zooplankton, and an even greater number of large fish eating those small fish. And this is going to be counterintuitive because you're going to be saying, well, wait a minute, what I've learned about trophic levels is that energy is lost as you go from one level to the next to the next. So how can you have a situation where at the base of the food chain, we have very few individuals present, and as we move up the food chain, the biomass seems to get more and more abundant? Yeah?
At any one time, there's very few phytoplankton, but they're being replaced so rapidly.
Right, so phytoplankton are able to reproduce at this incredibly high rate. So much so that at any given point in time, you see relatively few of them, but the few that you're seeing are reproducing like mad. Right, so there's more than enough to feed the zooplankton. The zooplankton are also reproducing very quickly, such that the small fish that are feeding on zooplankton, while not reproducing nearly as quickly as the zooplankton, are still able to take advantage of that resource and seem to keep churning and generating more and more zooplankton. And then as we move up all the way up to the secondary carnivores, you've got these piscivorous fish, these fish-eating fish that might reproduce once a year and might not reproduce every year successfully, that are able to feed on smaller fish that might have 2 or 3 generations per year. Zooplankton having multiple generations per week, and phytoplankton having multiple generations per hour. So you can get these inverted biomass pyramids in aquatic systems. One thing you cannot get is an inverted energy pyramid. You never have a situation where the productivity at the base is lower and the productivity at the successively higher rates, or higher trophic levels, is higher. Okay, so if you see an inverted pyramid like this, that's going to be an immediate tip that you're dealing with a biomass pyramid and not an energy pyramid. Any questions on pyramids? Know the difference between energy-based and biomass-based pyramids? And remember, energy is always going to have that time component. It's going to tell you the rate at which new energy is being produced.
You said energy pyramids can never be inverted.
Correct. Well, not in this universe with our laws of thermodynamics.
So there are different levels of primary carnivore. What about omnivore? Carnivore and herbivore. How would you place them? How would you pack them? Nice little world.
Ah, yes. How do we fit messy species like omnivores, those that needed multiple trophic levels, into one of these nice, simple sorts of, it's either a level 2 or a level 3, right? So the quick and dirty answer, the way people actually do it, is if you look at something like a possum, which will eat berries, it'll eat leaves, but it'll also eat insects, so it's simultaneously on the 2nd and 3rd trophic levels. The way you would do it is you would average over a number of different possum diets over the course of the year, figure out a fraction of that is based on eating plants, the fraction is based on eating insects and other animals, and then just sort of say, we have 70% opossum here, 30% of the opossum. Okay. That's how it's done in practice. Although, truth be told, most ecologists are lazy and pretend that omnivores don't exist in US because they're complicated and hard. But those that do the work sort of do that partition. I have time for a brief anecdote. So there's a famous ecologist at Columbia University who gave a talk on food web dynamics. He went through his introductory spiel on trophic levels, and he said, according to his framework that he used, he assumed that omnivores were rare. And at the end of his talk, I asked my question, which was, but omnivores aren't rare. So since they're not rare, why do you represent these models with them being rare? And he just said, because it's too complicated. And then afterwards at beers, I said stuff like bullshit, got really mad. He doesn't talk to me anymore. All right. I pulled this off an old exam. Sample exam problem relating to trophic efficiencies and relating to energy curves. So go ahead and take a crack at this. This is the kind of question I'll ask you again during finals week. I know, it's never going to be. What got my ass for?
Good man. No, it's not 105. You just divide 765 divided by 13,000.
What is that then? Yeah. From first to third, that's 667. Divided by.
It's over 5%.
international plus.
Yeah, that's biomass, because it's what, or measurements they gave us were. Say
One,
biomass.
2, 3, 4, 5, 6, 7, 8. Okay, due to the units. Is that legit? Here, let's see what you're doing. Biomass. Units of measure.
I didn't slash.
Alright, walking around, I see a lot of, energy pyramids being drawn.
Probably just copy that.
This is correctly. You guys just want to have a nice big wide base, representing 13,000. Roughly like that. Alright, so what's the trophic level, or what's the trophic efficiency from the first trophic level to the second trophic level? Okay, so 0.059. How do we calculate that? Okay, so we take the amount of energy at the first second trophic level divided by the amount of the first trophic level.
And the units cancel out.
You don't need to worry about that because the efficiency is going to be dimensionless. Okay? All right, count up from the first trophic level to the third trophic level. Okay, so what does that mean if you're a third trophic level organism in this food web, or this ecosystem? All that plant productivity and almost nothing for you. Only like 6/1000 of that is going to be available for you in terms of overall. All right. Now for the bonus round of this Eltonian pyramid. Is this a biomass or is this an energy-based pyramid? Biomass. In 10 words or less, why?
Units are for biomass.
The units are for biomass, I'd probably accept that because, yeah, there's no time component. There's no information about the rate at which you might be produced. But you're absolutely right because it is grams of carbon per square meter and not grams of carbon per square meter per year. It is a biomass based. All right, any questions on trophic efficiencies and energy pyramids? Eltonian pyramids. All right, for like the last part of class today, the last 15 minutes or so, I'd like to look at a couple different ideas or concepts around the idea of sustainability that you've encountered in the CIMI test. And there might be one new one I'm going to throw in just for fun. But sustainability has been a recurring theme throughout the chapter. So, sort of at the very beginning of looking at sustainable wood harvest on your Settleboro farm, we can look at how much, what do we set our thermostat at, as a way of sort of limiting how wood we're burning so that our forest doesn't get overexploited because, like it's wintertime. You could look at what we had to do if we replaced, so what if we had to replace some of our forests with wetlands to assimilate some of our sewage as ways of breaking it down? And this was sort of a way of introducing the idea of ecological footprint. And ecological footprint is this, it's a concept, it's a way of trying to think about how we as individuals use the planet in terms of not just the food we eat, a little bit of an exploration there with trophic efficiencies of diet, but there's a component of it that's related to the amount of energy that we use, the amount of physical land that we use to live in and work at, the amount of land used to grow the food that we consume, and the amount of land available for the to absorb the waste products we end up producing. So globally, we can sort of say, like, we can sort of go individual by individual, sort of average over, what's the typical American folk doing in terms of their footprint? What is the typical Bangladeshi's footprint? What is the typical Saudi Arabian's footprint? We can basically add all these up and sort of figure out the overall, how does this match up with what's called biocapacity? In other words, what's available on the whole Earth. And if you do that, you end up with the analytical solution of humanity's using approximately 1.6 Earths right now. You're like, well, that doesn't make sense. Right? You've got 1 Earth. How do you use 1.6 Earths? You've got 1 Earth.
On average,
Yeah, the average human on Earth is using 1.6 Earths.
That means we're using resources faster than we can replace it.
Okay, so it's sort of, the analogy here is like, you're making $1,000 a month, but you're spending $2,000. You spend $2,000 for it? No. Sure. Exactly, right? Why limit yourself? Just keep spending and spending. So the way this roughly breaks down is, there's roughly about 1.8 hectares per person, and the amount of available space per person seems to be going down minute by minute as we keep adding about 1.5 people to the planet per second. And so we have 1.8 hectares that can be per person that can be used in a sustainable manner. Forest products, fisheries, go out and catch fish, and then sort of there'll be enough fish to reproduce, so we catch those fish sustainably. We'll fish next year. So we can use our 1.8 hectares and those sustainably. Alternatively, we could use more than 1.8 hectares. In fact, we're close to 3. With the idea that we lose forest area, our fish stocks decline. Carbon dioxide accumulates in the atmosphere. So the ecological footprint is basically a framework that's an attempt to assess sustainability, and the overall assessment is humans not doing it. You've got to up your sustainability. So that's the concept in a nutshell. And it's sort of it's a simple concept. Sort of once you get into it, it's sort of relating the amount of earth you use on a per person basis and average that over all people. But I'm not entirely sure how accurate the assessment is that you use 1.8 hectares. That's roughly true. But in terms of trying to get into the sustainability of sustainable forest use on a per person basis, it actually is really difficult. And the person who developed these concepts back in the late 80s, early 90s, I saw him give a job interview in the early 2000s. And people really tried to nail him down on, like, where are you getting these data for the thresholds of sustainability? And he was pretty evasive about his answers. Which, of course, leads me to pretty person to be suspicious of the actual data that's coming out of these global ecological footprint analyses. Yeah.
So you think he gave a high estimate or a low estimate?
I think he did. I don't know if he gave high or low, but he specifically didn't really give a range of possible values or reveal what the assumptions were into how he came up with those values. So it wasn't transparent.
Okay.
So might be spot on, But, you know, as a scientist, I wasn't convinced with this approach of sort of giving numbers and not really saying where they came from. So, you know, I just don't know if those values are correct, but I do think that the ecological footprint does sort of speak to the broader issue of sustainability in a way that's relatively easy to understand, once you sort of work through your individual footprints. So, I mean, it has some utility. I'm not sold on its accuracy just yet. I could be convinced on this. I need data. But the ecological footprint idea sort of dovetails nicely with another concept of sustainability, one that actually goes back a lot further in history. This is this idea called the tragedy of the commons, briefly mentioned in your SIMI text. But it's been a very influential idea since it was first proposed in the 1960s. And the guy who proposed it, a guy by the name of Garrett Hardin, had made this idea famous in a paper he published in the journal Science in 1968. And what he did was he sort of started off with a metaphor. According to the metaphor, tragedy of the commons refers to any situation in which individuals acting independently and acting perfectly rationally, as individuals are, act rationally according to their own self-interest and actually behave contrary to the best interests of the whole group. So pursuing your own best self-interest can actually be detrimental to the broader group of which you are a part, and ultimately be detrimental to you. And in order to understand the idea of the tragedy of the commons refers to this specific incarnation refers to a resource that's shared by all people. And the original idea here was in small British towns, there was an area called the Commons in the center of town where people could raise their livestock. So back to our friend Gary Hardin. He basically described the tragedy of the commons by starting off with this metaphor. You have a number of people that live in a village, and they share a communal parcel of land called the commons. They're all herders. They all have livestock. And there is some limit to the number of animals that can graze on the communal land on a sustainable basis. So we could put, in this case, 20 cows out on our commons, and all is well and good because the grass is productive, it's able to reproduce at a rate such that standing biomass never really declines over time. So they have the same, because the cows are essentially eating the excess productivity. And all is well and good. However, while it might be, if you have 20 people in this village and you can put 20 cows out on the commons, it might occur to you that I need another cow, right? And what's the damage really of putting 21 cows out on the commons? It's just one more cow. And I'll get twice as much milk, and twice as much milk. Who knows what I can do? I can sell the excess, I can have more kids, farm more land, all kinds of good things can happen with that extra cow. But at the same time, as this individual's thinking about putting out an extra cow, his neighbor's thinking, you know, maybe if I just put out an extra cow, get a little extra thing. So everyone's sort of thinking the same thing, like actually I'd derive a little bit more benefit if I had another cow out there. And so what ends up happening is people put their extra cows out on the commons, which results in relatively rapid degradation of the resource. Everybody's cow ends up getting malnourished, and then they get sick, and then they die. There's no milk, there's no meat. But the thing about this is that every one of those herders in the village is thinking rationally and acting in their own self-interest, right? So, you know, the impact of everyone else is going to be small because I'm just doing this one little thing that shouldn't matter in the grand scheme of things. So that is the general metaphor underlying the tragedy of the commons. So Hardin applied this metaphor to other environmental resources, not just a commons area in an English village, but applied to things like air and air quality. So, what does it matter if I'm, burning my garbage in the backyard? you know, it's not like I have to deal with the air quality issues and I don't have to take it out to the curb, it's great. Or alternatively, things like fisheries. I know the limit on this lake for recreational fishing is 5, but no one's been out fishing all day and no one's gonna notice if I take a kid. So when applied to environmental resources in a more general sense, you can see pretty easily that each of these can be polluted or depleted by individuals acting in their own self-interest to the detriment of all. And so Harton's lesson was, or what we sort of derive from this is the idea that in order for there to be sustainability, we cannot have free and unrestricted access to finite resources. So otherwise it's going to lead to overexploitation. And Harton proposed a number of examples of how we can limit sort of the tragedy of the commons. One of his favorite examples was private property. Rather than have commons, why don't we parcel this up so that everybody has their own land for which they're responsible? But he explored other options as well. So, in addition to privatization, he looked at coercion or regulations. He had a really good turn of phrase I'll try to remember, but it's mutual coercion, mutually agreed upon. The idea that we all recognize that the commons can only sustain so much, and as a result, we're all going to agree that we're going to have this rule. It's the 20-cow rule. Okay? And I know that you have 2 cows, but you know what? That means you're going to graze 1 cow in the morning, and the other one's going to come out in the afternoon. You're not going to put them both out there simultaneously because you got the 20. And then the reason the commons ended up working so well in England for such a long period of time without the problems of overgrazing, and we still see examples of this today in small communities, is the idea of shame, right? The idea that if you know everybody and they know that you're cheating, there is social stigma associated with it. So in places where you have tight social networks, you don't necessarily need regulatory coercion. You don't need private property because you have basically social mechanisms that end up protected. So he explored a lot of these different ideas as ways of preventing tragedy of commons. So the idea, again, is that free and unrestricted access to a finite resource is going to reduce resource availability temporarily or permanently, and lead to overexploitation. So as you're driving around looking for a parking spot, you can think about the tragedy of the commons and the fact that there are more parking permits sold than parking spaces. 2 more I'll run through really quick. Your book also mentions ecosystem services, another lens by which we can sort of look at sustainability. Rather than looking at the environment as a thing out there, we can look at sort of the different things that ecosystems do to provide economic benefits to society. So we have things like regulating services, that is things like flood control, water purification, carbon storage, clean air, that is things that if you had to build factories to do these things, or otherwise spend money to do it, you end up spending a lot of money. But because ecosystems are doing this work for free, there's actual value associated with that. There's cultural aspects, education, recreation, aesthetics, stewardship, habitat. Sort of skip over the cultural ones. There's supporting services, things like biodiversity, photosynthesis, soil formation, food, and other things that ultimately support the ability of societies to exist. And fourth and finally, we have provisioning services, things like clean water, oceans and lakes and rivers that produce fish, forests that produce wood, insects that provide pollination services for food crops and wild plants. The idea that these ecosystems, again, are also working for us to provide these benefits. So ecosystem services is a way of trying to capture economic value of the world as a whole and represent that in terms of these supporting, provisioning, regulating, and cultural benefits. The last one, and I can't remember if this is in Semitext, but this is one that's gained quite a bit of currency in the last 10, 15 years or so. And it's another lens, it's another way of looking at sustainability, and this one's via a lens, it's called planetary boundaries. the idea here is that there are a couple of sort of key indicators of limits for the planet. So for example, we have sub-limits of loss of biodiversity, or sub-limits of climate change, is sort of acceptable limits. There's some limit of ocean acidification that would be sort of acceptable or reversible or remediated. Ozone depletion, nutrient cycles, including phosphorus and nitrogen, fresh water availability, land use, aerosols, and so forth. The idea here is to try to assess where we are collectively on the planet relative to sort of what are called sort of safe operating boundaries. Are we at or below these boundaries? So there are a couple things such as biodiversity, and for the global nitrogen cycle, it appears that we sort of exceeded the safe operating limits. And so we have later in the class, about 2 weeks, we'll start looking at some of the problems associated with the global nitrogen cycle, which is out of whack, why it's out of whack, and so forth. And then also with biodiversity loss associated with and then we've got some things that are, looks like climate change is just starting to creep over the limits of sort of the safe operating spaces as well. Now, in terms of these thresholds, what separates sort of the safe operating space from the danger zone, we have sort of this planetary boundary that we sort of draw in, and then we have sort of this zone of uncertainty. We don't know if there's going to be continual gradual declines or relatively rapid declines once we hit those boundaries. These are things we don't know because we haven't hit them. We can model it, we can estimate it, but we're moving into some unknown territory. Trying to figure this out. So with ecological footprints, with the tragedy of commons, with ecosystem services, with planetary boundaries, the general idea here is these are frameworks for trying to understand sustainability. These are lenses through which we're looking at the phenomenon of sustainability, ways of looking at the world. I'm over, which I hate to do, and I apologize. So I will see you all on Thursday.